Alright, so this problem says let P of t represent the population of a major city t years after 1950, as shown in the table and figure below. So you've got the years 1950, 1960, 1970, 80, 1990, 2000. So 1950 is year 0, population was here. 1960 was 10 years after that, 71,000, and you can see those numbers. So just to be clear, the independent variable t is years, and the dependent variable p is the population. We can see the graph over here, 10, 20, 30, 40, 50, and clearly it's going up. So part A asks, compute the average rate of growth of the city population from 1970 to 1980. Alright, so when we see that word average, normally we are thinking, let's add up a bunch of numbers and then divide it by the total number of numbers. And that is not the case here. This is the average rate of growth. It's not the average of a set of numbers. Well, yeah, that's good for us right now. So the way that you need to think of the average, and what that means, is the average rate of anything, the average rate of the growth of quantity y from time period t1 to t2 is equal to whatever the end value is, y2, minus the start value, y1, divided by, no, not x2 minus x1, t2 minus t1. So delta y over delta, yep, let's erase that and fix that there. There we go, t2 minus t1. So delta y over delta t, that's what you should be thinking and think of average rate of growth. Now, you might be thinking, that looks like a slope formula. Yeah, it is. It's the slope of the secant line between those two endpoints. So from t1 to t2. Great. So here they're asking for the average rate of growth from 1970 to 1980. And so this literally is a slope formula problem. Okay, so it looks like calculus, but it's really secretly algebra 1. So that means what's the population 1980 minus the population at 1970, and divide that by whatever the corresponding x values are, or the time values are. Now that would be, in this case, 30 minus 20, because that's the t values that correspond to those. All right, and you can plug those numbers in for the numerator and denominator. I'm not going to do all that in front of you. You've got a calculator. So final answer will be some number over another number, or if you divide it out, it'll be some number over 1. But it's interesting to make sure you're aware of the numerator value here. The numerator is it's going to be a population, and the denominator is going to be year. So it's going to be people per year. And you can look over here on the answer part, and that's what they provide for us, people per year. All right, so let's go ahead, fill in that number just in case you're curious about what it turns out to be. 11,102 people per year. Okay, great. Good for them. Let's go and look over here, part B. So part B says, explain why the average rate of growth calculated in part A is a good estimate of the instantaneous rate of growth of the city in 1975. Yep, I'm getting caught up here. Let's clear all this stuff out. So why is that average rate of growth from 1970 to 1980? So here's our graph over here. So I'm trying to draw a dot on 1970, 1980. It's not really working out too great, but that's that average rate of growth, and that's what that secant line. Why is that a good estimate of the instantaneous rate of growth? You might be like, instantaneous rate of growth, how could I measure how much something is changing instantaneously? And the answer is with limits. And you take those two secant, those points that you normally have for secant line, and get them closer and closer and closer. And as we saw earlier, the secant turns into a tangent line. So the instantaneous rate of change, or the instantaneous rate of growth, is the slope of the tangent line. So m tangent, slope the tangent line at whatever that point happens to be. So in this case it's at 1975. So they're asking, why is that secant line a good approximation for the tangent line, or for the instantaneous rate of growth? and it just sort of eyeballing 1975 there, right between 20 and 30. And so the secant line would look sort of like that black line right there. Or sorry, the tangent line would look like that black line. You can see those are pretty parallel. So remember, parallel lines have equal slopes. So the first question says the formula P30 minus P20 over 30 minus 20 gives the instantaneous rate of change? No, it doesn't. It gives, we saw earlier, that gives the average rate of change, the average rate of population change. So, not A. Part B says the average rate of growth from 1970 to 1980 equals the slope of the secant line. Yes, it does. That is correct. 1970 1980 does equal the slope of the secant line. But that doesn't explain why this is a good value for the instantaneous rate. So also wrong there. And then option C, the slope of the tangent line at t equals 25 is approximately equal to the slope of the secant line that passes through 20p20 and 30p30. Yes, ding ding ding, hooray, that's awesome. That's exactly what we're going for. Slopes of those lines are approximately equal. Alright, and then part C, not sure why they're asking us to do this because it's pretty much the same thing we did in part A. It says compute the average rate of growth of the city from 1990 to 2000. Okay, average rate of growth, that's change in y values over change in x values or time values. So this is literally going to be p of 2000 or whatever the appropriate t value would be minus p of 1990 over, okay, so it would be 50 and 40. So I could have written p of 50 minus p of 40, but I'm not going to go back and fix that now. So anyway, over 50 minus 40, the change in that time period. And in case you're wondering what that number happens to be, I think it's like 37,000 and some change. Great. So now we want to figure out, is this average rate of growth an overestimate or an underestimate of the instantaneous rate of growth at 2000? Oh, 2000. Okay, so instantaneous rate of growth. That means slope of the tangent line. And they want to approximate it. Okay, so let's go up here and let's draw the secant line from 1990 to 2000. So there's the secant line. Now the tangent line, we can see this because this function is increasing, it's getting steeper and steeper. So red line there is the secant line. Tangent line, I'm trying to make it a little obvious, it's going to be steeper there. Okay? And a steeper corresponds to a higher value of slope. Okay, so that's slope of the tangent at t equals 50. So they want to know, is that average, so is the thing that we found, the slope of the secant line, is that an overestimate or an underestimate? Well, the slope of the tangent line, like I mentioned a second ago, is steeper. Sorry, I should have fast forwarded this. Oh well. It's steeper than m secant, which means that m tangent is greater than m secant. Steeper slope means a bigger number, at least if we're dealing with positives. So therefore the secant line is an underestimate. It's not an overestimate. And then they want us to approximate the growth of the city's population in 2000. And I'll be honest, I don't know how they expect you to do that unless you have like a ruler or something like that to place on here, because the best way you can approximate slope of the tangent line at that point is to maybe draw a line and then literally do the rise over run. So you could possibly do something like that. The final answer is 50,000. If I were to guess, that might be this might be the type of thing where it's the answer key says something like it gives you a range of options, not a range of options, but some freedom. I'm not totally sure about the internals, but I would guess. So that we look back at the previous part C was 37,000. We know it's going to be steeper there, so it's going to be bigger than 37,000. So I imagine that possibly the answer is if you have like 40, 45, 50, 55, 60,000, all those are realistic numbers in the range. They gave 50,000 and they want us to approximate it, so I'd hope that there's some margin of error in the answers there. Thanks for watching. What we did is we looked at instantaneous rate of change and the average rate of change and how those relate to the secant lines and the tangent lines.